My name is Szulc. I flew here from Poland, which you guys probably might hear. I don't have a jet lag right now. Hope somewhere around 6, 5, maybe my body will tell me go to bed, so you have to wake me up, right? It should be fine. Apparently if I talk to guys from Britain, then sort of understand me. Here in the US, people tend to do what? So if I don't say something correctly, just ask me what the hell was that. I will try to speak in English more correctly. Alright, Apache Spark workshop, as I said, clone this project. So, the thing is, originally I intended this workshop to look a little bit differently than what we're going to have. So, Spark itself, it's built on a few modules. This picture is already obsolete. I mean, it's going to be in 2 days, no, more than 2 days. And they're going to release Spark 2.0. But nevertheless, there are some modules that you can use. And I was thinking that we'll just go module by module and show you guys how all those work, what you can achieve. But then I realized that basically all that, and you know, each module could be like 1 hour of our workshop. But then I realized it's something that you can guys do on your own. Basically, the documentation is pretty straightforward, and you can do it not here. This will be just a waste of your time. So, a few days ago, which was maybe a crazy idea because I didn't sleep a lot, I thought I would do something different. So when I started doing Spark 2 years ago, it was a completely different area. I call myself a veteran of early Spark adoption and production. At that time, if you had an error, you Google that error, you got 3 results, all of them in Chinese. And I know how to say my name in Chinese and how to say hello, and that's all. So yeah, I thought maybe I'll just try to sell you guys the knowledge that I got over 2 years. So we will go basically through the very initial module of Apache Spark, which is called core. It provides the API, which is like supposed to be the very low level API of Apache Spark, but people still use it. There are APIs which are higher level of abstraction, but knowing that low level APIs gives you 2 advantages. First of all, you might be the only person in the company who actually know it. And secondly, understanding the concept underneath will help you deal with problems in production if you might have any, and you will. So that what was basically my idea. So this is sort of a from zero to hero kind of workshop, right? So we're gonna start slowly from the very beginning. What's Apache Spark? What kind of problems it tries to solve? But we're not gonna go up high to those modules like Spark SQL or machine learning stuff. This you can guys learn once you know the core, right? So that's my intention of this workshop. I didn't have chance to do any pre-run back home, so we will know. Maybe we will exceed time, maybe we will be a little bit shorter, we'll just see. All right, so the question is, what is Apache Spark? Because some people might hear like, I heard it's cool and I can get raised if I know it. So Apache Spark is apparently a fast and general engine for large-scale data processing. And when I first read that sentence, I was like, yeah, so, okay. But doesn't actually tell me anything. So before we answer what Apache Spark is, let's try to answer why we should even care. What's the kind of problem we'll try to be solving with that tool? And that problem is called big data. Can anyone tell me what big data is? Like a definition. I read a great one. It's on Twitter, has so many retweets, and it goes like this. Big data is like teenage sex. Everyone talks about it. Nobody knows how to do it. Everyone thinks everyone else is doing it. So everyone claims they're doing this as well. But there are actually big data problems. So the big data problems. Big data is all about data, and you will learn that every day we generate 2.exabytes data all around the world. It's a number I really cannot comprehend. I mean, I can comprehend 10 or maybe 100, but 10 to the power of 18 is just mind-blowing. So I rather use this quote. So every 2 days we generate more data than we generated from the beginning of mankind to the year 2003. And you might be asking the same question I was asking myself, how is that possible? And I thought about it for a second, and I realized it's one thing: selfies.
No, it's porn.
Oh, porn, yeah. Selfies, yeah, porn. That's actually good business. Selfies, porn. All right. Anyway, so this is a capacity of data on which we cannot anymore use like a standard approach of software development, where I had my server and I said load some data, do some stuff on it, and gave the results to my business using Excel or whatever tool I'm using. Here, we are dealing with a vast, enormous amount of data that will not fit on your single machine. It will need at least few of them. And the problems that you will have are few, gathering and processing, but the ones we're going to focus on, especially when we talk about Apache Spark, are those two. So you can imagine that if you have just not one machine, but many, there will be a different approach to how to process that data. And of course, your system, well, it's not longer that you have your machine, it's down, you call your administrator, he just wakes up at 2 a.m., boots it up, and it's working. You're going to have a system, if you have let's say 100 nodes, at least one of them is dead, or seems dead because it's garbage collecting, whatever. So you need to have systems which are fault tolerant, so they can sustain an environment that is always faulty at some point. And on those two we're going to focus. So the question is, before we go into Apache Spark, what was before? I mean, is it it's not a new idea, right? Big data has been here for a long time. So what we had before Apache Spark? And we had a MapReduce. And MapReduce is a concept that was 12 years ago described in a paper from two guys from Google. Google wasn't the first company that was doing MapReduce. There were other companies doing MapReduce way before, but those guys were actually did the paper. 1 year after the paper, we had a fully fledged implementation of Hadoop. It is really not that long time between a paper and implementation, and that's probably where Hadoop problems has. But anyway, we had Hadoop, which is an open source implementation of MapReduce. Before I go any further, how many of you guys know what a MapReduce is? Okay, who doesn't know? All right. So quickly go through that. We're going to briefly here. So MapReduce is built on a concept that we had from functional programming. So it's a framework for processing parallel problems, blah blah, whatever. It's basically combined of sequences of two operations, map and reduce. And you know probably what a map is because you're on the functional programming conference. So this is map, and this is reduce. So idea is pretty simple. You go through sequences of phases, map and reduce, and so on. And this is how you develop your software on a big data using that paradigm, that model. Now, we'll go through the example, which is considered like a hello world to big data, which is a word count. I don't know if you guys know, there's a cool game, which is called, I can actually show you later on. It's a game you in a browser you play when you have to guess whether a name is the name of a Pokemon or a big data framework. And when you reach Hadoop, and for every framework of Pokemon, when you guess, they give you the final result. And if it's a Pokemon, you have the description of the Pokemon, who he is. Or if it's a framework, you get a short description of what the framework is. And a funny one is that on Hadoop, they say that Hadoop is a software created to count words. So because if you look for in Google for MapReduce tutorials, it's always this. So I thought, what the hell? I'm not going to experiment with anything else. I'm just going to go with word count. So the idea is pretty simple. You have some data, and now let's imagine there's a lot of that data. It's huge files of words, and we're going to want to produce the final result we want to have is the list of a pairs, when the key is our word, and the value is the number of occurrences in that big file. So MapReduce pretty much works like this. So we have our input, and just imagine it's a huge amount of data, right? So the first step that we're going to do is called split. It's a terminology from Hadoop. Why be using right now partitioning? Because it's the same concept in Apache Spark. But they just call it differently. They just call it a partitioning. So what we're doing here is we are just dividing those big files into smaller chunks on which we can work on, right? So the next thing, after we had that data divided into smaller chunks, we're going to do the first phase, which is called map. So what you are doing in this example is for every those little partitions that you had over here, we will take each of the words, and we're going to produce a word with a value of 1. So just think of it for a second. Imagine that this is the stuff, maybe still not Spark, but the concept applies in all big data solutions. So now imagine that you have a cluster, and that cluster only has 2 nodes, which are going to do your computation. So what will happen? You will take that very first split, that partition here, and you will run that mapping program on it. On the first node. Maybe a second node will take, I don't know, let's say that partition, and run that on parallel. So now you see that the program runs in parallel because each of the nodes take a small part of that partitions and runs that map function that we provide over here. The next part is called shuffling. Now what shuffling does, it basically takes all the data that was produced in the map part and transport it throughout the cluster, because it basically reorganizes partitions within the system. It puts all the values with the same key into a single partition. So this step is very expensive. Why? Because if you're working with like petabytes or terabytes of data, all that data will have to fly around the cluster. And not only that, in MapReduce in Hadoop especially, to actually achieve that, data flying around the network, saving, I'm going to take that data from this node and put it here. Implementation also requires that each of the nodes actually, before they do that, before they put that data over the network, they have to first put that on the I/O. So it's all really, really expensive operation. And at the very end, we have the second step, which is called reduce. Here in our function, what we are just doing, we are getting that list of key value pairs and basically sum the ones together. All right? Any questions? Should be straightforward. So, and the final result is basically just merging all together. So this is implementation taken from Wikipedia, copy-paste. But this is essentially what we just discussed a second ago.
I have a question.
Yeah.
Why isn't it called map shuffle reduce if we're always shuffling?
I don't know. That's called Google. I don't
Seems
know.
like you left out an important. They left out an important part. Of
I mean, maybe they knew it's the worst part of the paradigm, so maybe just keep it quiet and nobody will notice for a few years.
Well, if I might say, the shuffle is kind of like an implementation detail of what reduce conceptually is.
Yes, pretty much, yeah.
So it's a MapReduce.
But essentially, did you see any implementation without it?
Well, you don't implement your own shuffle.
Yeah, no. It's an implementation detail of Hadoop. We have a MapReduce, which was a paper, and then you have a Hadoop, which is an implementation of that paper. The question is, could you implement that paper, create a MapReduce framework without shuffling? It's pretty much impossible, because to do the reduce, you have to push that data throughout the network. So shuffle is like, it's not explicitly said, it is, but it should be there, right? All right, so this is in the map phase, we're going to just go word by word from each of the lines, and I'm just going to emit that key value pairs, our word and 1. And this is a functional programming conference, and the code is very imperative, but this is Wikipedia, so blame those guys. But basically, what we do is for each of those. So for each of the key, so each of the word, we got the iterator of those values, and we basically sum the ones and get the final result, and hooray. So this is how it looks like. So MapReduce is basically a sequence of those stages: map and reduce, map and reduce. Here, as you guys have seen, we had a partition where we run that function map, and it can run on parallel. After those all are being calculated, we have to shuffle that data throughout the cluster, and we got results. So, and if it's our final result, we just return it. If it's just one of our steps in our computation, we have to fire up yet another stage of MapReduce, and so on until we reach a final result. So now the question would be, still we don't know what Apache Spark is, right? Stupid workshop. But before we reach that, the question would be, why do we even need anything else, right? If you Google it, Hadoop was pretty much, 12 years right now in production? So people are using it. What's the problem? Yeah. So the problem is that, first of all, MapReduce provides a difficult programming model. And you guys might be saying like, what? I mean, this is straightforward. I mean, it's not the most beautiful code that there could be. Probably we could read it a little bit better. But it's, I mean, if I go imperatively, line by line, I will understand what's going on. The only problem is that this is Wikipedia, and this is the same code in Hadoop. And then I'm not even done here. It just continues like this. Vast amount of lines of code just to do a simple workout. Now imagine you do something more complex for your business. This is going to be fun. That's why I don't know any Hadoop developer who actually use this syntax. They all use higher abstraction languages like SQL and Hive and stuff like that. All right. Second one would be it suffers number of performance issues. And you might be like, this is oxymoron. Like it was supposed to be performance. So what the hell? So first of all, word count was really simple, right? If you have something more complex, then you now have a dilemma at this point, because how we conquer complex problems. Most of the time we divide and conquer, right? So this you got this notion. You want to do the same thing. You want to put like small stages. I will first map and reduce. Then I have some sub-solution here. Then map and reduce. Some sub-solution, map and reduce. But remember that every step has this shuffling operation, right? Which is really, really, really expensive. So what people tend to do, instead of doing those maintainable, readable stages, they squash them all together because they want to get as little, shufflings as they can. So you have to trade either your readability or for your performance. And well, if you're doing big data, you will always trade the maintainability and the readability, which pretty much sucks. The second thing is all the shuffling. As I said, not only shuffles the data throughout the network, it has to output everything to the file system, which is, as you can imagine, very expensive. If you have any algorithms that go they have to calculate the same data over and over again. So any machine learning algorithms or like PageRank algorithm, where when you read some data, you go for it. So if you have like a simple batch operation, when you load your tables from your bank's financial institution, do some report and just flash it, then it's okay. But if you have some algorithms when you have to load that data, do some calculations on it, then load another data, do some calculations on it, and then yet read that data one more time, and it's going to go through the MapReduce stage every single time. It's really, really, really tricky to make it perform really, really well. And the last thing would be the poor API. The API is restricted to the key value pairs, which I'm not going to go into details, but like a simple, and actually you're going to go into details. You're going to see that simple join operations in MapReduce, they have a lot of problems, and in Spark they are done pretty better and then well performing without you guys even knowing that. Overall, it kind of sucks. So the idea was cool, but when we reach the moment when we're doing something complex, there are a bunch of stuff that we have to deal with, and basically it all boils down to the fact there's a lot of shuffling going on, a lot of data flying around the cluster, and it's pretty expensive. All right, and last thing would be, and we're not going to cover that pretty much, but basically right now we have to be do batch processing, but also we have to live in a more streaming world. With Hadoop, you basically have to run a separate tool to do the stream, whatever stream processing that you have in your system. So you might imagine that you run your batch application every other hour, every other 24 hours, but you want to provide like a not very accurate values to the business every other 5 minutes. So you have to provide a more real-time solution, and then you have two code bases. The amount of bugs, just grow and grow. It would be nice to have a solution when you have just one API and you can use both for batch and streaming. All right, so now the Apache Spark Rescue. Before we go, just a quick overview. So we have 4 hours, right? Because I just realized there's a lot of to cover. All right, so we have our cluster. So just imagine a cluster is basically a place where we have some nodes and they are connected and they can compute some stuff for us. In Spark, you can use existing clusters. So there's Yarn, which was developed by Yahoo for Hadoop applications. There's Mesos, which is more, I would say, mature and complex cluster that can run enormous amount of jobs. Your clusters are expensive, right? So, and you might have not just one program using a cluster, you might have a few. So Mesos is really cool and really sort of intelligent to divide the resources that you have for your different programs running in your system. And Spark also comes with its own cluster, which is called standalone. And I'm a big fan of Ghost in the Shell, so it's standalone complex. I always think of it. Anyway, the examples that I'm going to see is going to be like with a standalone cluster because it's really easy to set up. But we can talk about the problems that you would also have in Yarn and Mesos. And apparently, if you want to instantiate a Yarn cluster, you need to actually have somebody who used to instantiate Yarn cluster. It's like a egg and a chicken problem right now because nobody knows how to do it from books or tutorials. All right, so in Apache Spark, we have something called a driver program. So there will be some words. I will just say that those are important because later on, if you're going to read some books and tutorials and going to watch presentations on YouTube, there are some words which are essential. So partition will be the first one. The driver program will be the second. So this is our application, whatever that is, running our program that we have, REST application, getting some requests from HTTP, and now has to fire up some calculations on the cluster. So this is our application. We also have a node in our cluster, one specific node, which is called master. That node is we're going to communicate with that node and talk to that node to actually fire our calculations. So what we do is we provide a URI. In a way, it's a Spark. The protocol is Spark, and then there's a host and port. And we create an object which is called Spark config, and we provide that master here. There's a bunch of stuff that you have to provide. Essentially, master is obligatory, and the name. So also provide a name for your applications. Later on, in your logs if something explodes, which job actually exploded. But that's pretty much it to actually run it. And at the very end, you create an object which is called Spark context. And now, I don't know if you guys see it, but when this is run, we're going to have this connection between our master and our driver program. So when this is instantiated, and let's say cluster is dead, then you're going to get exception right away, saying, I couldn't connect to that guy, what the hell? And bunch of our nodes in our cluster are called workers. So the terminology is also important because it's always confused in tutorials and books. And I also confuse it on the slides. So there it goes. So a node is called worker. So whenever you're gonna read about a worker, it's a machine, all right? But the process that will run your calculation is called executor, all right? So you're gonna run your calculation, and the calculation is gonna be sent to those workers, and they're gonna fire up a process, and that process is called executor. But people tend to use those names interchangeably, but they are not. All right. We are closely to doing our first exercise, but there are only 7 of them, so no worries. So the main abstraction that we have from Apache Spark is called RDD. It's yet another word that you're going to be hearing about when you read tutorials and books. And RDD stands for Resilient Distributed Dataset. So if you really want to understand the definition, you just have to read it from backwards. So it's, first of all, it's a data set. So it's just our data, which is distributed, all right? So that's only our data, a huge file we're going to work on, but it's also already distributed among our cluster. It lives in our cluster. And it also is also resilient, it's fault tolerant. So if, for example, that one of our nodes dies, the API provides us with a fault-tolerant solution that we don't have to worry. It will just work and survive the intermediate crashes that might happen during our calculation. But essentially, when you think of an RDD, you think of a collection of data. So RDD represents your collection of data that you have available on your cluster. All right? So let's see an example. Remember that Spark context? This is the SC here. I call a method text file, and I provide as a parameter a path to my file. This path actually reads from Hadoop distributed file system. It's one of the ways that we could read our files. And the thing that we get here, this logs, is of a type RDD. So RDD is a trait, and this thing is of that type. Now we don't necessarily have to use HDFS. We can even provide a path to a local file system. So HDFS, if some people don't know, is basically a file system which is distributed. So if it's run among few clusters, if you put a file on one node, it will just distribute that file over the other nodes in the cluster, and it's resilient. So it's not going to be like, it's going to put some small copies on that file, and it's configurable, but you can say how many copies of each of little pieces can be put on different nodes. So if one of your nodes dies completely, you can still recreate the whole file from other nodes in the system. So now you can use local file system, but the thing is that data on which you're going to work in have to be available for the workers, have to be available for the executors who are going to run your job. So you can use local file system, but at this point you are responsible to have that data distributed on all other executors, and also that data will be exactly the same data. Not that going to be a different version of that file. There are also other distributed file systems like Gluster, and it all works pretty neatly. So yeah, so pretty much.
What was that other one you said?
Gluster FS.
With the G?
GLUSTR-FS file system. When I was working with Apache Spark and we were using that API for whatever reason that we had, business reasons, actually Gluster was more efficient, at least for our problem, than HDFS. And there's also a method which is called parallelize. What it does, it basically takes your already existing collection in your driver program, and it can distribute it through your cluster. This is probably going to use it for like experimenting with stuff and just trying things out, not in real production code. So this is our example. So we have our logs files which are read, and this basically RDD represent a notion of that collection in our cluster. So next thing we're gonna do is we want to have them lowercase. So there's a method which is similar to collection API you have in Scala or any other probably language that deals with collections. So probably everybody knows how maps works. I'm not going to explain it. So now we have yet another RDD, and this one represents a new collection. Those logs which are now lowercase. You can still get access to those logs, but now you can also use the lowercase logs as well.
So the structure of an RDD is a collection, a list, a sequence, something like that?
We're going to get to that. But just, you're talking about implementation right now.
Well, you're doing a map across it, which seems to imply...
You think of it as a collection right now. Think of it as a distributed collection, but it's not collection, right? It's not, that data is not living on your program, right? We are writing that program, this is our driver program, but the data is represented somewhere else. But it gives you that notion that this is actually a collection, a data set, resilient distributed data set. So we can do other methods like filters and stuff like that. And this creates yet another RDD on which we can work on. So just to get you guys started, I have an example which I can show you guys. Yeah, so tell me when it works. Is it okay or bigger?
A little bit. Yep.
All right, so first things first. This is our Scala application. So basically, I extend app. If anybody, some people might not know Scala. Basically, just will run the program. So I'm doing the same thing I was showing you on the slides. So I create a configuration. I set a name, and this name is obligatory. Here, on all those slides, I just get the class name, and that is basically the name of the job that we'll be running. And the next thing, you guys remember that we were supposed to provide URI to our Spark cluster. But I'm not running any Spark cluster so far. What I can do is use this special syntax, which is called local. You can even use it like this. So local, what local does is it will emulate a Spark cluster running locally on your JVM. But it's just so you guys know, there, and we're going to talk about it later on, but there are some problems that you will just explode in production, and they will not explode when you're going to just play around with this local mode. Why? Because local mode is just emulate your Spark cluster on the same JVM. So if you're going to have any serialization issues in your code, you're not going to see it using that local mode. And in bracelets, you can provide the number of cores from your processor that you want to. Those cores will emulate the executors on your system. All right. If you're just gonna say asterisk, it means pretty much use everything I got. All right. So we have here a file which I prepared. It's all Shakespeare, everything that Shakespeare ever wrote. It's 5 megabytes of data. It's not really big data, but it's big enough for us to do this workshop. And yeah, pretty much so. So what we can do, I have that. So as you guys remember, I'm using this text file method, right? And I'm providing a path to a resource. And now on that representation of the data, I can say, let's say, call count, which will give me all elements, all number of lines in that file. I can collect all that data, which basically will return a list of all data from that collection. Now, you don't want to use collect on your terabytes of data, right? This would be just plain stupid. But for the purpose of testing or doing some staging environment, this might be useful. And here I'm just using a simple Scala collection take method, takes 5 results. And the last one would be, instead of doing that, we can actually tell Spark, give me 5 elements from that collection. And this might be something that we actually use. So you might have like millions of elements in your collection, but you want to just have a sample of it, just to know, just to present maybe to the user what we have in our system. And the take 5 will return that as a list on which you can print it out to the user. And so,
excuse me, why would you ever want the collect if you can do a take right on the RDD?
well, sometimes especially if you're doing testing your stuff or you're on staging, you want to just know how things work. You just want everything, right? Because collect will just give you everything. I'm here doing just collect and take 5, but on the same time I could just say collect and for each print me everything, right? All right, and I will yeah. So if I run SBT. Let's just run it. So if you type run, you get all the examples that you can run, and this one is called full scan. So number 2, it runs in the local mode, and we as you can see, I'm getting a lot of logs in between, because in that driver program I'm printing up stuff to the console on the same stuff. On the same time, I didn't configure any log4j properties. So, but those values are here. So if we scroll up, you see that collecting all elements, printing first 5, and there's also number of lines, and probably somewhere here that number is actually printed out. Basically, this thing works, but just is in between the logs. And the other example will be exactly the same thing, But one of the things that I did over here was just not only I took that collection, but also I filtered out any occurrences of lines that when they are lowercase and then contain Juliet, I'm only interested in those lines. And I could run it. Maybe this will be actually more, to provide more visual information. Maybe a bigger font, right? So I can see, every line with Juliet is here. So far, so good. Any questions? Yep.
So by default, the RDD is the text file split on new lines.
Yes, by default. There are other connectors which will work on different data. So you can connect Kafka, Cassandra, and stuff like that. But by default, when you use text file, because we read that data using a method text file, right?
Right, yeah.
So it reads your text file, which is basically collection of lines of strings.
Yeah, it just wasn't super clear in the beginning
Okay.
how the file was split into elements.
Okay, so so this is sorry. This is the file. We read that file with this text file method, and that gives us the RDD which represents that line in the distributed environment.
Okay.
All right. Any questions? Yep.
So when does this computation happen? When you define the RDD or when you actually do the collect?
In a second, right? It just will be explained in a moment. But before I do, can we just quickly, because I just want to have you guys, this is the simplest exercise we can get. So I just want to have that notion that everybody's up to date with what we have. So take that example, which is on the x1 path, so it's source main Scala x1.scala, and just make it a little bit different. So instead of printing all lines containing Juliet, have it Juliet, both Juliet and Romeo. It's a simple exercise. I just want to know every one of you guys can just run that thing and understand the very basics before we continue.
Sorry, did you already say this with both or with either?
So Juliet and Romeo, but we can do or if you want, whatever works for you.
Sure.
Yeah, just if you could, yeah. Let's just go with N. So it has to be both Juliet and Romeo in a single line.
Okay.
Sorry. I don't know why that doesn't fit on the screen. Because we have to move on, I'll just, maybe just let Pawel hear my lead. So what I did is I just extracted the first RDD representing everything. So all with Juliet is just that all filter and lowercase. And if we want to have if we want to have Juliet and Romeo, what we're gonna do is we're going to say, so I have a line, right? And that will only work if that line contains Juliet and that line to lowercase contains Romeo. Right? And we can Juliet and Romeo collect everything and print it out. So you guys see, this is our final result. It is essential that we understand the very beginning and we can run that example. So if you guys could just copy paste, for those who didn't finish, copy paste that what we have here, try to run it. So are there any people who are still not able to run it, compile it? Okay. Any help with that?
I'm getting a tuple that's printed out in the console.
Double.
I mean, I don't think I can run it.
You got the results? Yeah, I have. Yeah, I've gotten it as pretty as I can. I can't run it until it ends. It makes me sad.
Oh.
Some version of this right.
Oh, okay. Oh, yeah.
All right.
Can I just do an SBT run and we'll run that?
Because the time is still, even though it's 4 hours, pretty short. I have an idea that maybe if it's like going to be like one person having a problem, he can ask a fellow neighbor, and if we have like more generalized problem, we can work on it together, right?
Do I do that from that directory?
That works.
Okay, nice thing is that if we could do those experiments on REPL, and the cool thing is that if you have your Apache Spark installed, so this is where I have my Spark. There's a folder called bin, and there's an application called Spark Shell, which pretty much fire up REPL for Scala, but it will also instantiate a cluster for you, this emulator of cluster, and with that Spark context already created. So as you can see, it fires up, and I can do parallelize. 1 to 10 count. Let's just do count, and it works. So if you want to experiment with that, you don't always have to just create a whole new project. You can just run that. All right. Okay. So now back to your question regarding the efficiency, how it works, because. And the way I would look at it, we might be having wondering, all right, so is that really efficient? So I first read some files, everything, then I map lowercase that, and I have that created, so it's already a lot of amount of data, just to at the end filter out only errors. This might seem like not really efficient way to do it, but as it turns out, operations that you have on an RDD are divided into two categories. One which is called transformation, and the other one is called action. So transformation, what they do is they create new RDD, but it doesn't mean that any calculation is yet started on your cluster. It thinks of it as a recipe. So here we are building a recipe of what should happen if we at the very end run, let's say, errors count on our RDD, all right? We're just saying you will have to lowercase that, filter out the errors, and then give us the number of elements in the final collection. So this is just a recipe for our calculation, and how you can know which is a transformation and which is an action. Well, transformation just gives you yet another RDD, while actions will give you a final result. So like collect or count or first or take, those all gives you final result that you want to work on a Java program, a transformation just gives you yet another RDD representing your transformation that you're doing on your system. Yes?
Does text file fit into any of those, or is that just sort of that's what initializes the RDD?
Yeah, that's more like initialization. But you could think of it as a transformation because it still returns an RDD.
Sure.
So this is the example. So this will trigger the computation and give you the calculated integer. All right, so there are other, maybe I'll just move it. There are other, as I said, actions that we can use. Here one of them will be reduced. Not this one. This one. Here I'm just having some numbers from 1 to 1,000. I only filter out the even ones, and I'll be running some actions on it. And as you can guys see, the even numbers on line 12 is just our recipe, but I can run on that single RDD different actions on it, right? It's like a blueprint of what we want to do, and the actions will materialize our intentions. So I could, for example, run a reduce function, which is exactly the same reduce you're going to have on a collection. We're just going to run and run your function on elements of your collection, give you a sub result, and just run that function. And here you're just summing the elements. There's action called first, which just gives you the first element in that distributed data set. And we also have here, let's say, also an action for each, which will basically run some function that you provide. It's like a side effecting function, which will provide which will run whatever you provided as parameter. If you guys have any questions, just interrupt, right, in between, because I try to go fast as I can. Okay, so now the exercise is for you. We had that, so we have what set we can use. Let's just even this one. Use the even numbers in the example 2. Use the even numbers and try to find an action that will save those elements to your disk. It's pretty much saving it to a file.
You mean as a function on the RDD?
Yes. So because we had actions like count or reduce or collect, but now there's an action that will just save all your elements for the RDD into the file system. And I think I finally reached that point where people from US understand what I'm saying. So this is also good.
That was cheap.
That one, yeah, that was good.
No, it's actually my problem. It's like, you can imagine that you think you speak any English and you just try to, buy a ticket and somebody's like, what? It's like, I don't know. Maybe it takes time for me to. It's really troubling at the very beginning when I know the words, I know what I want to say, but just my tongue isn't, working with me. It's just like doing something else.
Somebody whose English is not their native language.
Okay, so I will just give you a hint right now. There's a method called save as text file, which takes a parameter path. But before we move on, just try to run and see what are the results.
So after doing the divide by 150 thing, is that what you're saying?
No, you can pretty much take the even numbers, right, and just call it a save as text file.
Oh, okay.
Bunch of
try
parts.
to save all 1,000. What?
Do we only want one text file?
It'll
you'll
make
see.
multiple.
Run it and you'll see it.
Yeah.
Yeah, you saw it. All right. That's the purpose of this exercise, to be surprised.
Okay.
Oh.
This directory.
Yeah.
Exactly.
Surprise, surprise.
When I tried counting the file, it says it's not a file.
All right.
That was not
So what we're gonna do right now is we're gonna call even numbers, save as text file. Not everything. Just need. Let's call it temp1, and let's just run it. Alright, and if there are any questions regarding Scala specific stuff, like I'm using a lot of underscore and stuff like that, just tell me. Because maybe, how many of you know Scala? That's probably the first question I should ask. So who doesn't know Scala? Okay. So whenever I'm doing something like, because probably this is the only tricky part. Maybe not. Okay. Whenever I'm doing something like this, it pretty much it would be the same like going like line. It's a lambda expression when I say line. And let's say like char. If it was a string, of course, because it's an integer. Okay, so maybe number to string, right? So this is a lambda expression that I provide to map method. But there's a shorter way of doing it, which is basically an underscore and to string method. So that's pretty much it. But if you guys have any questions regarding the syntax, just let me know. I know.
If you're stuck on Scala syntax, maybe you could post it in the workshop channel, and we could team help each other that way.
Yeah.
Yeah. So there's on the Slack channel there's a workshop /Spark.
Find that. Okay.
All right. So now if we run that program right now, so you guys see we said like even numbers save as text file and we provide path. So it's called some actions number 4. All right, so what happened? As it turns out, temp1 is a folder, right? If we go to that folder, we're gonna see a bunch of files. And if we try to look at one of those files, we're gonna get those results. But they are all not in a single file. And there's also one additional file, success. And you might be wondering why that is. So before I answer that, let me quickly tell you something about partitions, because it's actually really related to that. We remember when we were looking at Hadoop, and we had splits, and I said splits are what we have in Spark partitions. So this is exactly it. So if RDB represents our whole collection, the whole file, right? Whatever that we having in our cluster, whatever data we are working on. Partition is just a small subset of that data. That's pretty much it. And you will sometimes learn from books and YouTubes and stuff like that. They're going to repeat that. That number of partitions is tightly coupled with the level of parallelism that you can get in your system. And we're going to see in an hour or two why is that. But let's think of it. Let's try to just visualize what a partition really is. So this is our program. We read some text file and we just want to count all the lines, right? So those are our workers, node 1, node 2, node 3. And this is our file, which is distributed among the cluster. Now, think for a second. How would you run the count calculation on that single file? How to do it? Well, the easiest way to do it would be actually divide that file into smaller chunks, which are called partitions. And now you can run each of those small partitions on each of your nodes, right? So the code count here will be run for each of those smaller chunks. And this is happening in parallel. That's why we said that this number of partitions is tightly coupled to the level of parallelism that we can have in our system. So it's calculating count for every partition. And once it reach and have those sub results, it will just merge all the sub sums into final sum and return it as a result of that action.
So, sorry, I was going to ask, who computes the merging?
This will be done by master.
Doesn't matter.
And this is the next slide.
Oh, sorry.
Well, before that,
yes.
you said the number of partitions is related to the number of workers,
It's related to tightly coupled to the level of parallelism.
which is the number of workers, isn't it?
No. So let me park that question.
Okay.
All right, and I will answer it because you will see like if you provide the wrong number of partitions, you're gonna run into a lot of problems. This is one of those stuff you don't learn from books, and
Okay.
I will show that, but in an hour or two.
Okay.
All right. So one more time. Sorry. This is our driver program. This is our master. So we have a Spark context. We want to run. We have those logs, which are somewhere on the file system, and we want to run this count application. Now, you, I think, understand the concept of a partition, right? A subset of your big collection of data. Another word that you're gonna hear often when using Spark is called task. And task is nothing else than your calculation, which is here just simply count, combined with partition. All right? So in this example, imaginary example, our log files was divided into 3 partitions. So the files were divided into 3 chunks. All right? And what master node did was it took your calculations, which basically is serialized just to count. Calculate. When I say calculation, I mean just things you want to do on your system, right? Combined it with the first partition, and that thing we call a task, right? This is our data and our calculation. Took another partition, the same calculation, combined it, yet another task. Third partition, the same calculation, combined it, the third task. All right? On those tasks are serialized and sent throughout the cluster to your worker nodes, which will run the executors. All right? So this is my cool animation made on slides. It took me ages to do it. But this is the essential thing is that master will basically take that partition information, take the calculation information, put it into one box, which is called task. That task is being serialized, sent throughout the network to your executors. Each of the executor will calculate that sub calculation for that partition within the task, bring back the results to the master. The master combines the final result and send that to a driver, or does some other stuff with it, as we're going to see it in a second. Okay. So,
Excuse me.
yeah.
But with the save to text, there is no combining, right? It just
Okay, so I forgot about that. Sorry.
Yeah.
Sorry for that. We started with save as text, and okay. So now the question is how you would implement that save as text. If you were the Apache Spark developer, you have your data, right, on your small partitions divided, and the only action, the calculation, as I call it, the only thing that you do, you say just save it, right? So the way that they thought out how to do it is basically each of the nodes drops that data to a local file. So each of the nodes, each of the workers done it locally. That's why here, those files correspond to number of partitions that we had in our system. Here in this example, so each of the workers would just take that partition and save as text and just drop a file for it, right? Took partition, drop a file, another partition, drop a file, and it all goes into one single path. Why we have it right now available? Well, first of all, we are working on this Spark emulator. This is a single machine, right? But if it was still a cluster, you can drop those files into path which will be a distributed file system like HDFS or GlusterFS. So each of the nodes will drop it locally, but that folder to which they're going to drop is distributed through the system, so all other nodes and programs will see it. And that's why when all nodes are done, they send that information, I'm done to master. The master at the very end will put this file success. So this is information for you if you have some other system waiting for this job to be done. If I have that file success, then it means that the cluster is okay, it's done. And if you had some error, you would get like an underscore failure.
So in this case, there really aren't any results going back to master to be combined.
Not really.
Yeah.
No.
Okay.
Just acknowledgement.